Thanks for coming, everybody. Today we have Erin Dawson speaking to us more about tropical geometry, in particular maps of fans. So your third talk on tropical geometry. If you missed the first two, they're both on CSU algebraic geometry. So those of you that aren't here very often, feel free to check that out and subscribe if you like. I don't know, up to you. Take it away, Erin.
Okay, today I'm talking about maps of fans. So to start, we're going to build up to the definition of this, starting with defining a rational polyhedral cone. Sigma in Rn can be defined two different ways. So the first definition is the non-negative span of a collection of vectors. With rational coordinates. So, for example, we can have V1 and V2, and our cone would be the non-negative span of these. So in here, the other definition is the intersection of a finite number of linear rational closed half spaces. So with our example, we might have this half space and this half space, and our intersection gives us the same cone that we got before.
What do you mean by a rational half space?
Just a half space.
So you draw a plane of one dimension less than the dimension of your space.
Mm-hmm.
That's defined by a basis that has rational coordinates. And it's half of this one side or the other of that.
Okay, so some more definitions. The half lines inside the cone spanned by these vectors are called rays. Of our cone, sigma. So, in other words, these are one-dimensional faces of our cone. So, that line and that line, half line, are our rays. And then a cone, sigma, is called simplicial. If it is strongly convex, so pointy, and its dimension is equal to the number of rays. So, for example, if we had something that looked like this would be simplicial because we have 3 rays, and that's equal to the dimension, and it's pointy. And then something that would not be simplicial would be this one, because we have 4 rays, and it's 3-dimensional. So this one is a non-example.
What does pointy mean?
Like, it makes a point at the corner.
Oh.
That's the not very formal definition. But if you look at it, it looks pointy. Okay.
I think strongly convex means that if the vector is in the kernel, then it's negative, it's not. So
That's why it's pointy.
I don't, in my mind, pointy's a different property than strongly convex.
As far as I know, sigma intersection with minus sigma is 0.
So like if it contains a whole line, then it's not strongly convex.
Cool. Okay. A rational polyhedral fan capital sigma in Rn is a collection of rational polyhedral cones with the property that any two cones intersect along faces. So, for example, something like this. That cone too, or something like this. As a rational polyhedral fan. Okay. Now we want to define a weight function because we want to be able to say when our fans are balanced. And so we need to define what a weight function is. Sigma on a fan. Sigma is a function from a set of cones of sigma to the non-negative integers. So we're just giving weights to each cone. So for example, we give this 1, 2, 3. And so how we usually find these markings or find these weight functions is using the marking. So a marking of a fan
But how? So you give a weight 3 and 2 for the two-dimensional cones.
I just wrote them randomly.
What is for the ray between those? Is it?
You could also get those weights.
It's like a random.
Yeah.
Okay.
I mean, I did that randomly, but normally when we do that, we want to have weights so that our fans are balanced, is what we're going to want. But that's usually how they're, how you see them is numbers on the cones. Okay. So marking on a fan is a choice of an integral vector. On each ray. So, for example, if we had a fan that looked like this, and we wanted it to have a marking, we would have an integral vector along each ray So vectors in blue. Once a fan has a marking, we call it a marked fan. So if we are given a marking on a fan, that gives us a way to find the weight function of the fan, because we can define our weight function as the determinant of V1 through Vn, where we write the VIs in terms of the generators. Or just the generators of those. So for example, our cone is going to live in a lattice. And say we have a cone where the markings are 1, 2, go here. So V1 is 1, 2. And our V2 is 3, 0. So our cone goes like that. Using these markings, we can create a sublattice in our lattice by looking at multiples of these. So if we can make a new lattice using these. So if like from here we go over 1 up 2, and from the same type of thing to build a sublattice here, we can find our weight by taking the absolute value of the determinant of these vectors, which gives us 6. Or we can find our weight by looking at the lattice index between the new lattice that we constructed and our original black lattice. And so this lattice index is the area of this parallelogram in terms of lattice points, or you can count the number of lattice points inside our red lattice in terms of the black. So we would get this one, this one, this one, this one, and this one. And then the reason we don't get the ones on the top or the side or the other red ones is because all these red ones are equivalent in our lattice. Same with like these top ones are here. So our lattice index here would be 6, because there's 6 black to the red. So our weight function is 6, and we got that because of our marking, which is why we liked marked fans. Forgot to write what V2 was.
So this is a constant function, you're saying?
The weight function?
That omega sigma?
Oh, yeah, this is of the specific cone that you're looking at. Is that what you're asking?
You're defining value for tau.
Yes, for our cone tau. Okay. So now we're going to talk about balancing. So in the dimension 1 case, we've talked about this I've talked about this in other talks, but say we have something dimension 1, then we have our integral vectors going in each direction, and to check if it's balanced, we're going to sum the weights times our integral vectors or our primitive vectors, and if that equals 0, then we have a balanced fan of dimension 1. Our dimension 1 balanced fans are always going to look like these tropical lines that I've talked about before, that we're going to be looking at through the rest of today. And then, so once our dimension is higher, so say we have a fan where we have that cone, a cone like coming out towards us, and a cone going like out backwards. We want to check, so for our one-dimensional case, we are checking the balancing around the vertex. For dimension higher, we want to check our balancing around a one-dimensional cone. So if we want to check the balancing along this cone, we would project this down, and we get back to our one-dimensional case, where now our one-dimensional cone is the vertex. And so we can check our balancing the same way we have before, where in each of these cones, we have our normal vectors, which are integral vectors. So the red ones would be in the cone going up. Those would project down to a primitive vector. And same with vectors on the other cones of this band. And so when we want to check balancing of something with dimension greater than 1, we reduce it down to the dimension 1 case, check the balancing. So when a fan is marked, we have these vectors, so it makes it easy for us to check balancing. So I have a lemma that says that if we have a marked fan, sigma with a codimensional 1 cone, tau, in our fan, then there is a unique and top dimensional, so the biggest cones that we have, cone sigma. Then within each sigma, so if we have this fan where we have sigma 1 and sigma 2, sigma 1 and sigma 2 have 2 markings, like for sigma 1, there's a marking on this side and there's a marking here. But we aren't looking at any markings in tau, so this is tau. So we're only looking at the outside markings for each of our cones in this case. Then sigma is a balanced fan. If the sum of these markings are in the span of tau. So if we sum marking 1 and marking 2 together, we want it to be in the span of tau, and that means that this fan is balanced. Okay. So if we let sigma 1 in our M and sigma 2 in our N, then we can do both fans, then a map F from the support of sigma 1 to the support of sigma 2 is called a map of fans. If F is the restriction of a z-linear map, so a z-linear map means that we have a linear map where the coefficients are all integers, and we're restricting this map to each cone when we're mapping. So, for example, we can have in R2 to R1 to R. If we have our first fan sigma 1, this we can use our function letter f just mapped to the y value, then we just get the line, because this part of the fan will go here, this part will go to this vertex, this part will go here. Or we can have something like fan like this, mapping to a fan like this. And so what we would want with a map of fans is that it would map cones to cones. And with this second example, it shows that that's not always true. But what we can do is we can subdivide one of our fans to make a new fan, such that our map of fans maps cones to cones. So here we could subdivide our first fan like that, and just have the identity map sending it to the second fan. And so for the rest of the talk, we're going to assume that all of our maps of fans maps cones to cones, because you can always subdivide to get this property.
So you're only subdividing the source, right?
Yeah. Technically it didn't say just the source, but I haven't seen any where they subdivide the other. But it didn't specify source, so I don't want to say that for sure.
Okay.
Okay, so now we want to define what's called the local degree.
Okay, can I ask, so when we define weight, there was nothing to do with the marking, right?
No, but
But
markings give an easy way to find the weight,
Oh,
because we can look at
So-
we can define the marking as the lattice index, or the that we talked about.
lattice index. So okay. So we define the weight function using determinant, but that's only for the.
That determinant is equivalent to the lattice index.
Okay, okay.
Because lattice index is giving you the area, and determinants also give you
Yeah,
area.
that was my question.
That help?
Yeah, I was wondering what if dimensions were.
Okay, so the local degree, given a map like above, so from sigma 1 to sigma 2, this map of fans, is denoted the multiplicity P of F, where P is a point in our sigma 1. Is defined as the weight of sigma 1 for the cone that P is in, divided by the weight of sigma 2 for the cone that the image of P is in, multiplied by the index of the lattice index between sigma 1 lattice and the sigma 2 lattice. So I'll do an example here of the local degree. So if our first cone has markings 1, 0, and 0, 1, and then we have F, 0, 2, 0, 1. F is mapping to a cone where our markings are 1, 1, and 1, -1. We can find the weight of both of these. So the first one, the area that we're going to get is 1. So the weight of sigma 1, which is equal to 1, which we could also solve by doing the absolute value of the determinant of these vectors, so 0, 1, 1, 0. And then the weight of sigma 2 is the absolute value of 1, 1, 1, -1. Am I supposed to be a 1? This gives us weight 2 for sigma 2. And for our lattice index, our first lattice is the black one, and then we can create a sublattice over in the image here using the blue. And we get the lattice index is 2. So if we put it all together, our local degree of this map at point P is 1 divided by 2 times 2, which is 1. So the local degree of this map is 1.
How did you choose that lattice? Can you explain one more time for the index?
The lattice index,
How did you get the lattice?
the blue one, the blue circles,
Yeah.
Since our V1 and V2 map over to W1 and W2, they're creating a new sublattice over there using 1, 1, and 1, -1 as generators. And so, like, from here we can go over 1, up 1, or over 1, down 1. And same thing as we continue to make. I circled the lattice points of the blue lattice.
But where did you get the 2 for the lattice?
The 2, because if you look inside, like, this blue lattice, like, region, there's 2 black points, or the area of that is 2.
So you're calculating index between 2 lattices, right?
Yeah.
But so I guess I can see the 1 lattice there. But what is second lattice?
The black.
Okay, I see.
Okay. So now, another definition, a balanced fan is irreducible. If it can't be decomposed as the sum of 2 balanced fans. And in this case, in terms of fans, by sum we mean the union of couplings. Where we, So, for example, an irreducible fan, that one's irreducible, while if we had this fan, that is reducible because we can take this fan, So now, if just like before, we're going to let sigma 1 and sigma 2 be two balanced fans. Of the same dimension. Then, if we assume that sigma 2 is irreducible, and we have F, a map of fans, then for any point Q in the interior of a maximal cone, of sigma 2, then we can define the degree of the map F to be sum of all P over all P such that F of P map to Q, P maps to Q, we're summing over our local degree. So if we have in sigma 2, we have a cone sigma that has Q in it. There could be multiple cones in sigma 1 that all have a point that map to Q through F. We're going to find the local degree for each point over here and add up all the local degrees, and we get the total degree of the map to point Q. Okay. So, in a special case, if sigma 1 and sigma 2 are marked fans, there's another way to calculate the local degree. If V1 through Vn are markings on rays in sigma 1 and W1 through Wn are markings in sigma 2, then the local degree is equal to the determinant of M, where M is a matrix that expresses F in terms of the basis V1 through Vn and W1 through Wn. So we're going to go to the same map of fans that we found the local degree of and check to see if this gives us the same degree and explain how this matrix M works. So for example, if we have our same things that we had before, where B1 is 1, 0, B2 is 0, 1, and that is mapping to W1, which is 1, 1, and W2, which is 1, negative 1. To make this matrix, you can break it up into 3 different matrices, where the first thing that we want to do is take our markings over here and get them in terms of orthonormal basis for R2. So they already are the orthonormal basis for R2. So our first matrix is the identity, because we want to take 0, 1, 1, 0 and get them in terms of 0, 1, and 1, 0. And then our second matrix, we want that to map 0, 1, 1, 0 to 1, 1, 1, negative 1. And so we can do that by doing 1, 1, 1, negative 1. But now that is giving us something in terms of our orthonormal basis, 0, 1, and 1, 0. So that would give us a point in terms of, the orthonormal basis. So now we want to multiply by a matrix that will get us back to an answer in terms of our new W1 and W2. And so we want to represent 1, 0, and 0, 1 in terms of 1, 1, 1, negative 1. And in order to do that, we need 1/2, 1/2, 1/2, negative 1/2. So that last matrix is then getting our answer to be in terms of our new basis. If we multiply these all together, we get the identity matrix, which didn't make a lot of sense to me at first until I multiplied something by it. So if we're taking our V1, we want to send V1, which is 1, 0, to 1, 1. And so if we multiply 1, 0 by the first matrix, we get 1, 0. And that is just scaling it. And then the second matrix is sending 1, 0 to 2, 0. Which is giving us the point 2, 0 over here. But now we want, oh wait, no it's not. It's giving us 1, 1, sorry. Multiply 1, 0 by 1, 1, 1, negative 1 gives us the point 1, 1, which gives us this point, or that vector over on that side. But we want that in terms of W1 and W2. So we multiply it by the last matrix. It sends us to 1, 0 again, which is telling us that we have 1 W1 vector and 0 W2 vectors, which gets us exactly where we want to be. So our matrix M is the identity, and the determinant of the identity is 1. So we get the local multiplicity is 1, which is what we got before, which is good. And so usually making this matrix is a little easier than doing all the lattice index. So this is a nice trick when we have marked fans to calculate the degree of the map. So now we're going to talk about a little application. So we can use, we can compute how many tropical lines go through 2 points. As a degree of a map of fans. So the first thing, we're going to sketch out how to do this. The first thing that we need is this fact that M02 trop R21 is isomorphic to R2 cross M05 trop. So things in this left-hand side look like a tropical line with 2 marked points. But we're gonna number all of them to label it. And then a map to R2 that sends this gamma, calls gamma, to a line where the marked points contract to just points 1 and 2. And so that's what things look like in the left-hand side. In the right-hand side, it's R2 cross M05 trop, and M05 trop consists of irreducible, balanced fans with a marking. So for example, 1, 2, 3, 4, 5, where our marking is the length of the middle. And so those two things are isomorphic, and we're going to use that. We're not going to prove that they're isomorphic. So now we're going to look, we need a map to look at the degree. And so our map that we're looking at, phi, we're going to go from M02 from R21 to R2 cross R2. And that is sending our gamma and our map to the x-coordinate of our first marked point, the y-coordinate of our first marked point, the x-coordinate of our second marked point, the y-coordinate of our second marked point. Forgot to say. Over on gamma, we know the lengths of these. So we know the length from here to here is L1, and the length from here to 2 is L2. Which, when we go through F, that means we know that this is L1 and this is L2. So, if we're looking at sigma in M02 drop R21, this sigma looks like we have an x value, a y value, L1 and L2 to represent it, because our x and our y give us the x and y coordinates of our first marked point, and then our L1 and our L2 give us how we're getting to our second marked point. So we can represent sigma as x, y, L1, L2. So in order to represent this map in terms of a matrix, we want something that is going to land us at x of 1, y of 1, x of 2, y of 2. And is taking in, or we're multiplying by x, y, L1, L2. So that's how we can represent our sigma. And so in order to get x1, when we multiply by x, y, L1, L2, we want 1x and 0 of everything else. And in order to get y, we want 1y and 0 of everything else. And then in order to get to x of our second marked point, we want to start at x. And then in order to get to the x value of the second marked point, we need to move over L2. So we want 1L2. And then similarly for our y, we want to start at the y value of our first marked point, that red, and move down L1 to get to the y value of our second marked point. And so this matrix is representing our phi. So if we take the determinant of it, it'll give us the local degree of f at phi. And the determinant of this matrix, since it's a block lower triangular, is the determinant of this times the determinant of that, which is 1. Well, absolute value, we get 1. So we know that the focal degree of f at our sigma is equal to 1. And to finish showing that this total degree is 1 is you would have to show that there are no other cones that go through these 2 marked points, so there's no other graph and map that go to the same marked points. And once you do that, you see that this is the only cone that goes to these 2 marked points. So our total degree of the map is 1, which tells us that there's only 1 tropical line through these 2 marked points. Thanks.
Questions? I have a question. So that fact there, is there a non-tropical version of it for the moduli space of maps to P2 or something?
I don't know. I'm pretty sure the isomorphism is coming from you use the forgetful morphism to forget the map. But I'm not for sure if that would still work. I don't know. Yes.
So the first time you defined local degree, you had this point P. Could you scroll back to that? Where was P in this picture? And
Somewhere in this code.
okay, and is there any point that would have a different local degree in this cone?
No.
Okay.
Yeah. If it was on the edges, I think it would. On the inside, yeah.
I guess when you, after subdividing cones with the n rays must go cones with the n rays, correct?
Is that it?
Can you scroll down to the defining map M? That map M. Yeah.
Yes.
So there's n vectors for the first cone, and then n vectors for the second cone. So I guess after subdividing, also always happens. Maybe.
If they're both marked of the same dimension, yes.
So sigma 1, sigma 2 are the
On the fans.
fans in the same dimension.
All right, let's thank Erin again.